Yeah, thanks, Ifan, for the introduction. My name is Qing. I'm currently assistant professor in University of Michigan. Actually, I just finished this slide this morning, so the result is quite. The first time I'm talking about this, a part of the first time talking about this. So I don't think I need to introduce the trend of generative AI in the past 10 years, right? From language models to vision generative models, these diffusion models, and they really enables a lot of remarkable generation capabilities from language generation to text to image generation and video generation, and it also accelerated AI for scientific discovery. So in this talk, I want to focus on the generalization. So the central question here is that how close is a distribution learned by the generative or deep learning models approximate the true distribution of the data. So here P theta is the distribution learned by a neural network, where theta is the parameter of our neural network. And P data and is something like a ground truth distribution that we want to learn. And we assume that our data has some ground truth distribution here. So I think I mean, this problem seems to be easy, but actually in practice, there's a lot of challenges. So one of the question is that how many samples we need to learn the underlying distribution of our data, and how does it scales with the model capacity, right? And this question is important because we don't know the underlying distribution P data, right? We only when we're training our models, we only get a finite number of samples, where n is the number of samples and xi is the training sample point. And if we don't carefully choose our model capacity, right? For example, if our theta deep network is very large, our theta is very large, then we will be overfitting to the empirical distribution, right? And in many cases, if we don't have like sufficient samples, the empirical distribution doesn't equal to the true distribution, right? Then we will just memorizing and we don't generalize, right? So, and what kind of mechanism really enables our model to generalize when we're training with finite samples is something that fundamental we need to understand, especially if you look at the models we are training nowadays, where they have a remarkable generation abilities that they do not just purely reproduce the training data, but actually they can generate new contents and how this kind of generalization emerges. So the second question is auto-distribution generalization, right? So in many cases, we claim that, for example, the in-context learning ability in transformers, we can, using in-context examples that we don't need to fine-tune our model, we can generalize to other distributions. But does transformers really have this kind of auto-distribution generalization ability? And how can we understand this? So this is something that we want to answer in this talk. So first of all, the first example I want to give is the diffusion models, right? We are trying to answer the first question through diffusion models and try to understand how diffusion models generalize when training with finite samples. And then I will try to answer the second question through an example on the in-context learning. So the first example is the diffusion models. I think in the past talks, right, people already talked a lot about diffusion models. I don't think I need to spend much time on this. So essentially, the important part of diffusion models is a reverse diffusion process, where you start from a Gaussian noise, and if you learn the score function really well, you can reverse this process and to generate data that hopefully follow the underlying distribution of your data, P data. And in practice, when we do this, ideally, if we really want to learn the P data, then we want to minimize a loss like this, right? Where the minimization, where the X is drawing from the distribution of P data, and we want to minimize this population loss, right? We want to minimize everything with respect to the expectation of our data. But again, because we don't know the underlying distribution, So what we do in practice when we're training diffusion models is that we are not going to minimize this loss. Instead, we are going to minimize over an empirical loss over finite number of training samples, right? So where xi is the sample point and n is the number of samples. So you're going to minimize something like this. But you think about this, so if you make your model capacity really large, right? You make your model to be infinitely large, then when you're training this loss, right, you're going to overfit to the training data. Then actually you are just learning the empirical distribution, not a true distribution. Then the question is that why diffusion model is able to generalize in this setting. And we really did some experiment to study this. Actually, we find indeed the generalization strongly depends on the model capacity versus the size of training data. So here we are fixing the model capacity, where the x-axis in this central figure is showing you the number of training samples. We're training the number of training samples, and we plot this and fit a curve for different kind of data set, like say for syllable A and FHQ, etc. Right? And where the x-axis is showing you the number of a training sample divided by the intrinsic dimension, where the intrinsic dimension is fixed. We're changing the number of training samples, and the z-axis is showing you the generalization score. So we basically, when we generate a sample, we try to compare the nearest neighbor in the training data to see whether we are generalizing or memorizing. And you can see that actually when you have a limited training samples, your model actually is indeed learning the empirical distribution and memorizing. So if you look at sorry, do you know whether this pointer is, can I using this laser? Oh, oh, okay. Thank you. Got it. Uh, So if you look at the thing on the left, right? So the generated sample bed model in this case actually is, and if you compare it to the nearest neighbor in the training data set, right? When you have limited samples, actually the model is indeed overfitting and memorizing the samples. And in this case, a model is learning the empirical distribution of our data. However, if you look at the right-hand side, right? So when you're increasing the number of training samples, actually the model is start to generalize. And then if you look at the generated samples, the first row is showing you the generated samples, and the second row is showing you the nearest neighbor in the training data. And actually you can see that actually there's a significant difference when you're increasing the training data size. So this suggests that actually model has this kind of transition from memorization to generalization. And then maybe a very simple way to explain generalization is the following, right? So you can consider where we're increasing the number of samples, and eventually you make the n go to infinity, right? So eventually the empirical distribution will just approximate the true distribution. And you might think might be the reason that the model generalized. But however, this kind of simple explanation will suffer from a curse of dimensionality, especially we are learning a distribution in high dimension, right? If you're learning a distribution in high dimension, actually you would need exponentially many samples for this interpolation or approximation to be happen, right? So, so this is a little bit like called this curse dimensionality. But however, if you look at the experiment we did, and if you look at the number of samples you need to enable generalization, actually the number of samples that the model transit into generalization actually is much smaller than the worst case predicts, where you only need around, like say on a safer data set, where you only need like n equal to 10,000 or something. So which is much smaller than the worst case predicts, because D is a number of pixels. So the pixel number could be very large. Then the n, in the worst case, could be extremely large. So then the question is, why there's a gap, large gap between the theory and the practice, right? Why we can do generalization, achieve generalization with finite number of training samples. way smaller than the worst case theory predicts. So this is the first question I want to address in my talk. And then the second question I want to address in my talk is about in-context learning and especially this autoregressive and the transformer models, how they can do auto-distributed generalization. Uh, uh, so what's the intuition that they can do this kind of auto-distribution generalization, right? So in comparison, so where diffusion models is learning a joint distribution over all the xi to xt, right? Xi is x1, xt is an index. So instead, transformer, this kind of autoregressive model, they break this through into conditional distribution, and then they are trying to learn the conditional distribution through the next token prediction, right? So what they do is that they given a bunch of conditions, like for example, in the next token prediction, right? They have this kind of example A to B, B to C, and then the model knows that when you have an input, a new query, you can do the correct prediction, right? This is another example, right? If you have a interval from A to C and B to D, right? Then the model knows that when you have an input query, the output from M should be going to O and so on and so forth, right? So this is basically the next prediction. And then actually people and the model can also do this kind of in-context learning, and they generalize this kind of a token to in-context examples. And this is an example, right? You have some like this kind of uh, uh, symbols, and then you given a bunch of in-context examples where, for example, this symbol has a color of yellow, and this one is green, and you're given a bunch of in-context examples, and then you put a new query, and then they will be making a prediction of the corresponding color. And on this case, right, you are predicting the shape, right? The triangle, the circle, the square, etc. Right? You are given in context examples, and then you want to and you leverage this to do auto distribution generalization. And it seems like transformers actually can do this OD task just by leveraging this kind of in-context examples, right? And they actually don't do any fine-tuning. They don't need to do weights update. But actually, you're just given this kind of paired in-context examples. And even this kind of auto distribution of the training data, you can make seemingly making the correct predictions. So then the question is that is transformer or is this in-context learning really have this kind of auto-distribution generalization? And when and why we can achieve auto-distribution generalization? There are many works trying to study this. They are trying to interpret this in-context learning ability as a gradient descent, implicitly as a gradient descent on the weights. But there's no definition of what is the distribution we are generalizing to, right? So I think if you want to properly study auto-distribution generalization, you need to define what is the distribution you are generalizing to. So this is a question we want to study through a simplified model. So our answer way to tackle this is that we are trying to assume a ground truth distribution that is simple enough and it has closed and analytic forms. And we're building on this ground truth distribution to provide the correct insight why the model is generalizing. So specifically, central to this talk is that we are assuming that our data is following this mixture low-rank Gaussian distribution. And then we want building on this distribution, we are trying to study the generalization with finite samples and also distribution generalization abilities of in-context learning. So essentially, this is a little bit mathematical, but essentially, in your mind, this mixture low-rank Gaussian is basically the data is drawn on a union of subspaces, and each subspace is a Gaussian. And we'll talk about this in more detail in later. So we are trying to leverage this simple data model to demystify generalization in diffusion models and also auto-distribution generalization of in-context learning. So first, I want to talk about the generalization in diffusion models, the first example I give. So again, we come back to this figure where I talked about this earlier, right? So what we see is that there's a large sample complexity gap, right? In practice, the generalization is achieved when you only have like need finite number of samples. But in the worst case theory predicts, right? If you have arbitrary data distribution, actually the number of samples you need is exponentially large. So then the question is that how can we understand why in practice we only need a finite number of samples to enable generalization? So our claim answer to this is that so although the worst case is showing you that the number of samples can be exponentially large, but we are not learning arbitrary distributions. So the distributions we are learning in practice is usually on images or videos, and they are low dimensional, right? So and this is a experiment did by researchers Tom Gunst's group like 4 years ago. They are developing some approach to probe the intrinsic dimension of different image dataset. And they find that even on ImageNet, the intrinsic dimension is around 45 or something, right? So which means actually the intrinsic dimension of images actually is much lower than the ambient dimension of your data. And so that's actually gives the intuition why the generalization, actually the number of samples we enable generalization is not as the worst case predict, because in practice we are not learning arbitrary distributions. We are learning some of these kind of low dimensional distributions, and that's why actually we believe that the number of samples to learn the underlying distribution is not growing, is rather growing linearly with the intrinsic dimension, where the intrinsic dimension is much smaller than the ambient dimension. And that's how the model are generalized. However, for image distribution, right, is usually the image data set is lying a union of a nonlinear manifold, which is very hard to characterize. And that's why actually we want to, if we want to study this sample complexity, we want to start with something simple. And this leads to us to consider this, sorry, this mixture of low-rank Gaussian distribution. Right. So if you look at this, so basically, so here we make a further simplification. So we assume that the mean is 0, and we assume that the covariance is degenerate, where UK is basically the basis of each subspace, right? So here we are consider a K subspace, where each subspace actually is governed by the covariance matrix sigma k, where the sigma k is degenerate matrix, it's low rank matrix. So UK describes the columns of UK describe the basis, which is R dimensional, right? It describe the basis of each subspace, and here we are assuming the subspaces actually they are orthogonal to each other. And if you look at this, actually, this mixture low-rank Gaussian, where the R, the dimension R, captures the intrinsic low dimension of the data. On the other hand, so because this is a Gaussian for each subspace, right? So the distribution is simple enough. Actually, we can precisely uh, analytically derive the optimal posterior mean for the mixture Gaussian, and it will be something looking like this. So before I proceed, actually, I want to show you that another evidence that why the model is low dimensional. So actually, we did some other experiments. There we are doing diffusion models based on this denoising autoencoder formulation. So this is a variant of a score matching formulation where we're learning a denoiser DAE from mapping from the XT, which is the noisy image at the T's level, to the clean image. And this is actually equivalent to score matching based on the Tweedy's formula. And we compute the rank of the Jacobian at noise level T. But so this is the GT, G theta is denoting you the Jacobian for the X theta. And actually, we evaluate the numerical rank ratio of the Jacobian across all the noise levels. And what you find is that if you look at this rank curve, right? So x-axis is showing you the noise levels. So where a higher SNR is closer to the clean image, and the lower SNR means we are much closer to the noise. And then the y-axis is showing you the log of the numerical rank divided by the ambient dimension. And what you can find is that actually in the intermediate noise level, the rank of the Jacobian is very low, right? And we believe that actually the lowest point is corresponding to the intrinsic dimension of the data. And usually the rank ratio at the lowest point is beneath 10 to the minus 2, right? Which means actually the rank ratio, if you consider the pixel number is a 1,000 something, actually is around 10 or something, right? It really captures the intrinsic dimension. And this is something important we'll be leveraging later. But let's go back to this mixture of low-rank Gaussian, right? So this distribution is really captures the intrinsic low dimensionality of our data. In the meanwhile, it's analytically trackable, right? We can derive the optimal posteriors for this distribution very easily, right? And that's why actually it's much easier for us to, as a first example, to derive some bonds. And moreover, we also did more experiment inspired by the posterior mean, where we try to approximate this UK using the training data set. We use training data set to approximate the UK, and then we can draw samples from the optimal posterior mean, and this is a comparison by approximating based on the training data set, just analytically derived the denoiser on the training data set compared to the generated samples of a practically neural net, the samples drawn from a practical neural network. So if you look at a simple data set like a fashion MNIST and MNIST, right? The first row is showing you the generated samples from UNet, and the third row is showing you the generated samples from this mixture low-rank Gaussian, where the denoiser is analytically derived. So you can see that actually the generated quality is pretty close, right, in this case. So which means that actually the mixture low-rank Gaussian is indeed captured in essential characteristics of image distribution. However, if you run this experiment on like a more complicated data set like CFAR or FHQ, the analytically derived denoiser captures the core structures, but it loses the fine details. So which means that actually it's acting only as a local approximation. It doesn't capture all the details of images, right? We still need this kind of nonlinear models. And okay, so this is a good. Then the remaining question is that how can we derive a mathematical theory that reflects how many samples we need to learn the mixture low-rank Gaussian? So towards this, so let's consider the case where you have a one Gaussian. So you just consider the mixed Gaussian distribution where the capital K is equal to 1. You just consider the simplest case where you only have one Gaussian mode. And in this case, based on the optimal posterior mean, let's parameterize our neural network something like this. That is inspired by the optimal, sorry. let's say it's inspired by the optimal posterior. And once you parameterize your neural network, something like this, and you actually can show by plugging this back to the training loss, where our training loss, I have to go back, is something like this in the first row. So once you plug x theta using our parameterization, actually you can show in this case, actually the training loss is equivalent, exactly equivalent to the PCA problem, right? So now, okay, we show this is a PCA problem, and this is a very classical problem that is well studied in statistics. So actually, there's exactly a phase transition. How many samples we can learn the basis U, or not learning the basis U, right? So what we can show, borrow from the classical theory, is that when the number of samples is larger than the intrinsic dimension, right, we can learn the basis. And if the number of samples is smaller than the intrinsic dimension, we cannot, right? There's exactly a linear dependence of the intrinsic dimension and the number of samples, right? And actually, we can show this through numerical experiments. And this is a phase transition in PCA, and this is when we're training the diffusion model. So there's a slight difference. And then, okay, so we show the results for k equal to 1. How about we have multiple subspaces, right? In practice, the data could be clustered, right? It's not just a single subspace. So what can happen? And what we can show is that when you have multiple subspaces, then actually the problem can be shown equivalence to the classical subspace clustering problems that we can also derive the sample complexity that is depending linearly on the intrinsic dimension. So this is a theory where we are able to show for multiple subspaces where we parameterize our neural network, something like a mixture expert, and we can show that actually the training loss is equivalent to subspace clustering, that there's a linear dependence on the, sorry, it should be N and R. I made a mistake at the end. And this is not just holding on simple distributions. Actually, we try to justify this kind of linear dependence on real data set. We tried on all the data set and like CPR10, FHQ, etc. Right? We are trying to fitting the curve, a linear dependence between the intrinsic dimension and the number of samples, right? You can see that actually the curve is actually fitting pretty well. So when you are fitting the n with the intrinsic dimension squared, actually the curve, the fitting is worse. So which means that even on the real data set, and we are training your practical UNet, actually the sample complexity dependence on the intrinsic dimension actually is almost linear. So this confirms our theory of this kind of a linear dependence. Moreover, this type of understanding actually can also shed light at how can we control and steer our generation. So if you believe there's a linear network can do this kind of denoising, actually this can also shed some light that how can we control and steer our generation. So the intuition is that if you assume that our model is linear, so then if you perturb your generation by using like a column of your low rank component, right? So actually the low rank component will be corresponding to some semantic meanings in your data, right? Like gender, hair, color, etc., right? So actually, if you perturb your generation using the low rank components, actually they are indeed changing the output uh, um, in changing the different attribute of your model, right? For example, you can use one component, the U1, to steer the gender, and if you change the strings where the alpha is denoting the, sorry, I made a mistake. Alpha should be lambda here. So essentially, if you're changing the strings, it will be linearly changing, steering your output, right? It gives you some interpretability and controllability of your model. So in practice, the model is not exactly linear, but actually you can compute the first order approximation and do a singular value decomposition of the Jacobian, and using the low rank components of the Jacobian to do this kind of steering, right? And in practice, by adding more engineering components, actually we can enable more complicated generation. We can do a localized and precise steering of or image editing of your model. And we can show that actually this kind of steering has a lot of nice properties where we have a homogeneity that you find a one steering vector on, like for example, one image like this female or this male, and then you can actually transfer to edit other images, for example, this female to change the eye size, etc. And moreover, if you look at the components, right, they are orthogonal to each other. So the attributes actually are disentangled. So actually you can do compositional editing and you combine two editing directions together. Actually, you can simultaneously changing the eye size and the smell without disturbing other part of the image, right? Uh, Moreover, so far everything we focusing here is about a linear model, right? But in practice, people are using nonlinear models. So how can we study something more complicated? So this is our more recent work. So we are trying to study this kind of mixture, learning the mixture Gaussian by using a two-layer nonlinear like this kind of a nonlinear networks where W1 and W1, W2 are both learnable. And we assume that our sampled training data are sufficiently separated, then we can show a stronger result to unify the understanding between memorization and generalization. So the linear models can only study generalization, but how about we have a unified structure framework to study both memorization and generalization? Actually, our more recent work, we show that actually we can do this through this kind of a two-layer nonlinear network. And what we show is that in the memorization regime, where your model is highly over parameterized, and in that case, you can show that the optimal solution actually will be something like this. So the weights, each column of the weights are storing the training data in the weights. And this is how the model memorized, right? It's storing the training samples in the weights. And now the network is acting like a associated memory type of network, right? And that's why they reproduce the training data. And when the model generalizes, we can show is that in the model needs to be under parameterized, and then the optimal way is actually capturing the data statistics. So here each block of this matrix here is storing the the underlying mean and the covariance of your mixture Gaussian. And that's how the model actually generalizes. So here is some illustration. So we run some experiment on the image data set for this this nonlinear autoencoder. And we can see that actually, indeed, when the model is in the memorization regime, so the model actually, the weights, the column are very sparse. And each column, a non-sparse column, actually are storing the training data there. And when the model generalize, actually they are indeed learning the data statistics, right? If you look at each column, actually they're corresponding to the means plus different directions in the covariance matrix. And essentially they are learning the data statistics of the underlying distribution. So this is why the model memorize and generalize, right? And moreover, so a more interesting thing actually is that actually if you know that the weights have this kind of structure, actually this also shed light of how the model learn the distributions of your data. So specifically, if you look at the bottleneck layer of this nonlinear DAE, so this is H is the representation learned of your through the model. And in the memorization regime, right, if your model is just storing your training data, and say if you're using this model to generate a new sample, and the new sample will be just reproducing one of the training points, right? And if you consider its representation, right, the representation actually will just using the closest sample to represent it, right? So you only have a one spiky point, which means that representation would be very sparse and it'd be very spiky, right? We only have one component to like retrieving the stored sample to reproduce the generated image, and then the representation will be very spiky. Well, if you consider the generalization, right, the representation is much denser because you are generating a new sample. You are combining all the data statistics together to generate the sample. That's why the representation will be is much denser. So you can think that the representation will be a signature of a memorization generalization based on the spikiness and the denseness. So actually, we did a histogram trying to show you the representation spikiness and the denseness. Here, this blue color is showing you the memorized, giving you an example of the memorized representation, right? You can see that actually the memorized representation is very spiky. There's only one point standing out here. But if you look at the generalized representation, right, the generalized representation is much denser, right? And then actually they can be separated, right? If you do the histogram, the density of the generalized and memorized representation, right, they actually have a strong difference there. And this is the result we did on unconditional diffusion on syllable A. But if you do larger models like a stable diffusion on Lion dataset, this is a more salient difference between memorized samples and generalized samples, right? If you look at the representation, the generalized representation actually is much denser, while the memorized representation actually is very spiky. So how can we leverage this? Actually, we can leverage to do memorization detection, right? We just based on representation spikiness, we can do memorization detection. And what we did is that we test this very simple approach where we just put a threshold, right? We press a threshold of the spikiness on the representation. So if it's spikiness is larger than a threshold, we say this is a memorized sample. We just do something like this. It's very, very simple. We don't need to train, and it's also prompt free. And if you look at the time efficiency, right, our method is much more efficient than all the existing memorization detection approach. And actually, we can achieve much state-of-the-art results using this very simple approach by understanding the representation structures in the data between memorization regime and generalization regime. And moreover, this kind of understanding and can also shed light of how we steer our models. So when the model, say we're using a steering vector to steer the model output of specific attributes. So here we are trying to add to make the person older, for example. And when you are steering a generalized model. So when the model is trained on a generalization regime, so actually if you adding the strings, right? Actually, the people are becoming older smoothly, right? So smoothly linearly corresponding to the strings. But if you look at when we are steering a memorized sample, so there's almost no changes of the output, right? So there's a difference of how the model works here. And we also try this. This is another example, right? We tried by adding an oil paint to the image, right? We're changing the strength, so the generalized sample actually will be changing smoothly. But if you look at the memorized samples, right, so there will be a very brittle or a very abrupt change when steering the model, right? So there's actually the memorized and the generalized models samples are actually operating in a very different style, right? It provides some understandings of how the model can be controlled and working here. So how many time do I have? Uh,
It's like less than 5 minutes.
oh, okay, sorry. I think I probably cannot finish all this. I'll try to be fast. So I think the second part where I want to try to address is that how can we leverage this mixture Gaussian to study the auto-distribution generalization abilities in in-context learning, right? People arguing that in-context learning has this kind of auto-distribution generalization abilities. So here we are using a test, this linear regression as a test bed. It has been widely studied in the literature, right? I think Define and Ying Hall has worked on this. So here, our starting is the problem is very classical. So here we start starting the linear regression problem, where the W is a task vector, right? But however, I think in a lot of the previous works, people are arguing that in-context learning is essentially doing gradient descent on the weights, and there's no characterization of what kind of distributions we're generalizing to, right? So our setup to study this is that we're studying the linear regression. We are also starting a very classical setting where this one layer linear attention. And this is actually like a standard setup in the literature for theoretical studies. And we're testing on new on test pairs where the W is drawing from another distribution that is different from the training distribution. And so to study auto-distribution generalization, so I think we need to make some assumption of the underlying distribution that can understand how the model generalizes. So here again, we're assuming the task vectors for our linear regression task is generated from a mixture of low rank Gaussian. So basically, they are lying on the subspaces, and we are starting in a setting where our training task vectors is drawing on the US and US perp, and where US and US perp are orthogonal, and the test subspace is can be characterized by something like this. So it basically has some angles. It's an interpolation between the two subspaces of US and US perp, where theta is the subspace angle. And then we want to see what would be the generalization error would be. And I think this figure basically essentially tells you the whole story. It gives you a very nice geometric understanding of how the in-context learning is generalizing. So I want to ask you two questions. So the first question is that, so suppose, so my setup is that we have two subspaces, right? So we have this is a US and this is US perp. And the first setup is that suppose we are drawing samples on one subspace. We only draw from one subspace, and we train the transformer to do in-context learning. And then in the inference phase, we are testing on UT, which is a different subspace. The subspace has an angle with the original training subspace theta. And then my question is that what would the generalization error be? So what generalization depends? The error will be depending on. So first of all, I think it must be depending on the intrinsic dimension of the subspace, right, which is R. I'm not sure I'm describing this question clear. So the answer here is that if you train on this US subspace and you try to generalize to UT, the generalization error actually will be depending on the intrinsic subspace dimension multiply the subspace angle, right? So when you're having larger subspace angles, then the generalization error will be larger, right? So how about the second setting? So we consider a second setting where you draw your task vectors from two subspaces. So you have a US and US perp. You will be drawing randomly from the two subspaces. Like for each, like you're drawing one subspace with probability 1/2, another 1/2 you're drawing from the other subspace, and then you train your transformer. And in this case, you have UT, which is a linear interpolation.
Sorry to interrupt
Okay.
because it's already out of time. So
Okay.
yeah, perhaps you can just finish the presentation like a little bit quicker.
Okay. Sure. Yeah. So if you're generalizing to the subspace, which is an interpolation between those two subspaces, actually in this case, the generalization will be equal to 0. So which means actually this is a interpolation type of result. When you are training on two orthogonal subspaces, actually the generalization, you will be generalizing to the convex Hall of the whole subspace, right? So basically the conclusion is that when you're training on a single subspace, your generalization error will be depending on the intrinsic dimension multiply the subspace angle. But when you are trying on multiple subspaces, actually the generalization will be, the inconstant learning will be generating to the convex Hall of the training subspaces. So this actually tells you that the training task diversity matters, right? You want to increase the task diversity to enable a better auto distribution generalization. I think this example is very simple, but it gives you the intuition that how the in-context learning works. So there's a lot of mathematical proof of this, but I want just to skip. So this is the two works that I just talked about. And my conclusion here is that actually this mixture of Gaussian can serve as simple test bed to understand generalization in generative AI models. Thank you.
Okay. So because of the time limit, we can allow just one question. Is there any question from the audience? Okay.
Hi, Professor. I have a question about in the high dimensional data, if the data from various distribution, even if the data is the amount of data is large, so will it affect for the generalization or memorization?
So I think that in my talk, the message is that the number of training samples to enable generalization is depending on the intrinsic dimension of the data. It's not depending on how many I think it's also depending on the model capacity. So you want to train your model on the in the under-parameterized regime where well, I think this captures this. You want to make your model capacity smaller than the number of samples, and in the meanwhile, you want to your number of samples larger than the intrinsic dimension. Yeah. So this depends on three parts: training sample points, the intrinsic dimension, and the model capacity.
Thank you.